Hey everyone, today's lesson is on systems of equations, but this is not the whole thing. We'll also get to Diophantine equations. Systems of equations is essentially, think of it as different variables being put together. So on an xy plane, on an xyz plane, and so on and so forth. Many of you are familiar with this, yet for those who aren't, this will be a learning opportunity. But I'm sure for those who are familiar, you certainly may not be familiar with Diophantine equations, which in my opinion are, although not interesting, fairly important to know, as you may run into them in certain problem sets. Now, systems of equations with one variable, x is equal to 3. Well, the solution for this is fairly obvious. X is equal to 3. Not much to do about it, and it's not really a system, just one component. Now, on the other hand, if we have x plus y is equal to 3, well, that's going to be a linear equation. Y is equal to 3 minus x. Now, we can't really solve for x and y. It's a parametric relationship. But if we are given two systems of equations with x and y, say for example y is equal to x plus 2 and y is equal to x minus 1, well, there is a point where those lines intersect, and that is the answer to both equations, or rather that is an answer or a coordinate that will satisfy both equations. Now to find this, well, in this case, they don't intersect. Why? Well, because their slopes are similar. So why don't we add a 2 here? Now, if we add a 2 here, we can find this out. We simply subtract from equation 2, with, of course, this being equation 1, this being equation 2. We subtract from equation 2, or rather, yes, we subtract from equation 2 equation 1. So, in our y part, it'll be 0y is equal to x minus 3. So we'll get that x is equal to 3. And we sub it back into this, and we get y is equal to 5. And simply it's 3 plus 2. Now, as you can check with the other equation, being equation 2, 5 is equal to 2 times 3, 3 being x minus 1. And we see that indeed the point 3, 5 fits this equation. Now, as you saw before, we can't solve this equation on its own, simply because, well, if we have two variables, we need two equations. And you'll see the same thing for three variables. If we have, for example, 3x plus 2y plus 5z is equal to 0, and we have 4x plus, say 7y is equal to 10z, plus 10z is equal to 3, and furthermore, if we have 5x is equal to 9y plus 10z is equal to, let's say, once again 0, well, that's a bit messy, let's fix that 7. We get something quite interesting, a linear equation. Or not a linear equation, but a systems of equations. Why? And a solvable one too. If we had only two, we could think of these as being, if we only had two equations, we could think of these as being planes, wherein these two may intersect should they not be parallel or even be the same plane. And when these two do intersect, they would form a line of intersection, and we could thus solve it parametrically. I won't get into that as it's a bit more complex, and it's not really the focus as we want to get to Diophantine equations, but so forth. Now, we have three variables, and of course, three equations, and thus we can solve for a single point rather than a line. And once again, if we just had one equation, well, we just have the equation. No answer to that. Now, if on the other hand, not if, let's solve for this. Now, we can have this equation 1, equation 2, equation 3. Now, just to make this easier, and let's eliminate the z's, because equation 2 and equation 3 have the same coefficient, and equation 1 is a factor of the other two. So now, if I can zoom out, I seemingly cannot. That is fine though. If we take equation 2 and subtract from it equation 3, well, we get negative x is equal to minus 2y, I believe, is equal to 3. Let's fix up that y. Ooh. Yeah, because the z's cancel out. And then you do 4x minus 5x, negative 1, 7y minus 9y, negative 2, 3 minus 0, 3. And now we do 2 times equation 1 minus equation 3. And in doing so, I apologize, we get x minus 5y, I believe, and we'll check in a second, is equal to 0. That's essentially 6x, being 3x times 2 minus 5x, yes, that's 1, and 2y times 2, 4y, minus 9 is 5y. Yes, we were correct. And 5z times 2 is 10z, minus 10 is 0. So we've successfully eliminated the z's. Now what? We, once again, set up two equations. Equation 1 and equation 2. And now for us, this is a linear system. And in this case, we can just add up equation 1 and 2 to get rid of the x, as they're of the same magnitude, but of opposite signs. This will give us 7y is equal to 3. And of course, y is equal to negative 3 over 7. Now, substituting back into the either equation 2 or equation 1, we get simply, rather than y, let us substitute it into equation 2. Since that has a 0 and it will be easier. We have negative 3 over 7 as x minus 5y is equal to 0. Now isolating for y, we get y is equal to 3 over 35. Or negative 3 over 35. Whoops. I do apologize for that. Now, these are fractions, but we could once again substitute both x and y into one of these equations and solve. But that's not really the point of this. You could do it on your own, but there's nothing much of value to learn there. Now, so far, we've established that if you have an n number of variables, well, you can sort of, I suppose, solve for that if and only if you have n number of equations. That is, your number of equations have to be equal to your number of variables. However, there lies another method, the Diophantine equation, wherein you have some number more variables than you have equations, but I believe it's 1, but I'm not sure. And yes, you can solve. So, for example, say you have 4b plus 5g plus 9r. And you have 4b plus 7g plus 8y. And of course, the first one is equal to 0, the second equal to 2. Now, Have I made a mistake here, is the question. And the answer is, I believe not. You can solve this parametrically, indeed. Can you now? Now that is the question. I believe you can solve it parametrically, of course, but I'm unsure as to whether or not you can get an exact solution. Of course, you can test that on your own and see if you can find any numbers that give you exact solutions. But we'll do this first on our own. And let's not make it so easy. Let's not give ourselves 4b. Let's say plus 9b. Now, as you can see, two of our variables here are, this would not quite constitute a Diophantine equation, I believe. I would like a moment to think. Let us do another equation. If I may have 1 second to develop this and ensure that it works fine. In essence, this, I should mention while I'm doing this, allows you to solve questions with, say, more variables than you have equations. Now, in our case, say we have 1p, and by the way, this is a question from Waterloo. I won't tell you which one, but it is one. P plus b plus g. That's equal to 13. Similarly, you have b plus g plus y. That's a poor y. I apologize. That's equal to 17. Then you have p plus g plus y. And I believe all of those are correct. Once again, let me double check. Yes, that's correct. Now, this, you have 4 variables and 3 equations. So what do you do? Well, I suppose I should introduce this now. By pigeonhole principle in this case, and this is how you identify Diophantine equation, you see that you have a total of 9 elements, yes? And further, you have 4 variables. Now, if each element is repeated twice in each equation, if each variable is repeated twice in each equation, you will have 8 elements. However, we have 9. This thereby indicates that one variable is repeated 3 times. And that's a short introduction to pigeonhole principle as well. In this case, it's g. Now, we can get rid of g. If we do, let us first label these, equation 1, equation 2, and equation 3. If we do equation 1 minus 2, this being p minus y is equal to negative 4. And if we do equation 1 minus equation 3, this becoming, I believe, b minus y. If I can make sure. Yes, this would be correct. Being negative 6. And finally, equation 2 minus 3. In this case, being b minus p is equal to negative 2. And that is the case, yes. Now, what do we do in this case? Well, we add up the equations such that they have 3 terms. And now we will get 3 equations and 3 variables. As you can see, we have 3 variables. So let us once again label this equation 1, 2, and 3. If you add equation 1 and 2, you get p minus 2y plus b. P minus 2y plus b is equal to negative 10. Similarly, if you do equation 1 minus equation 2, you will get 2p minus y, I believe, minus b is equal to negative 2. And indeed, that is 2p minus y minus b is equal to negative 2. Now, if you do equation 2 minus 3, you will get, or rather 2 plus 3, you will get 2b y minus p minus is equal to negative 8. And if I can verify that, yes, that is correct. Now, herein, you get 3 equations with 3 variables as stated before. And you can solve this, and eventually, you will get a parametric answer. That is, these 3 graphs, or rather these 3 planes, as indicated by equation plane 1, plane 2, and plane 3, all intersect on one line, and thereby may be solved parametrically, not in the full answer. I am unsure as to whether the Diophantine equation in the 3-dimensional case, or at least in these cases, will give, in the standard polynomial case, it will give a non-parametric answer. However, you're free to try on your own and see what variables you can get and use, and see if you can get a non-parametric one. But in this case, as I have tried it before, it will be a parametric answer, and you're free to solve as extra practice. I hope you've learned something and enjoyed the process, and I hope to see you next time on this channel. Thank you and goodbye.